A tree diagram is one way that we can express a series of events. So we can use tree diagrams to determine sample spaces and help calculate probabilities of events. An example here, if we choose one burger, one side, and one drink, how many combinations are possible? So there are 3 different kinds of burgers. We could have a beef burger, a chicken burger, or a fish burger. Think of them as sandwiches. Sides, we could have fries or a salad. And then drinks, we could have a soda or juice. So with a tree diagram, we always have an anchor or a start. And then we can create the tree by just taking one of our options and listing out each of those options on their own branches. So beef on the first branch, chicken on the second, fish on the third. And then we go to the next choice, sides, fries and salad, fries and salad, fries and salad. And then the last choice for our drink. And you can see the different branches that we have. Now, in order to come up with the sample space, how did they get 12 possible outcomes? At the start, we follow the branches until we get to the end. So we have a beef, fries, soda, drink, cola. We can write this as beef, fries, cola. We could do it again, beef, fries, juice. We could do it again, going back to the beef, salad, cola, and so forth. I'm going to do one more kind of off the cuff, chicken, salad, cola. So we could write that chicken, salad, cola. And we can write all of these out just by following these paths. And each one of these combinations is an outcome in our sample space. And if we count them, that's how we get 12 total outcomes in our sample space. Take a moment and create your own tree diagram to determine the sample space for flipping 4 coins. That's what we did at the beginning of this lesson. Let's take a look at the sample space and see what are the outcomes. What is the total sample space for flipping 4 coins? And to get you started, we'll have our little start node, is what we call the little dots. And then we can have the first coin, the penny. We either have heads or we have tails. And I'm going to make these branches pretty big because I've got to do this 4 times. Once we flip the penny, then we flip the nickel. When we flip the nickel, then we flip the dime. And once we flip the dime, then we flip the quarter. And we're going to do this for every single branch. So on the tails too, nickel. Pause the video and fill out that tree diagram on your own. And when you resume, you can see the answer. Although this is pretty messy, I apologize for that. We can follow these branches again to get our sample spaces. And I drew a line between them just to show you the first half of the branches and the second half of the branches. And we have a total of 16 outcomes. We'll talk a little bit later on in this chapter how we can count them without having to do the tree diagram. But it's still good practice to be able to create a tree diagram because that can help us in a lot of different situations. But our sample space for flipping 4 coins consists of all of these different arrangements of heads and tails. All the different possible arrangements of heads and tails. Great! Let's take a look at some more questions. On a multiple choice test, with 4 possible answers for each question, what is the theoretical probability of answering one question correctly if you guess? So how many correct answers on that question? 1 correct answer out of 4 possible answers. So our probability is 1/4, or if we want to write that as a percentage or a decimal number, 25% or 0.25. If 2 dice are rolled 1 time, find the probability of getting a sum of 7 or 11. Maybe we need this when we're playing a board game and we need to land on either the 7th square or the 11th square. And we want to know what's the probability we're going to get there. Well, before we do that, we need the sample space. Here we're talking 2 dice. not just one. So one die has a sample space of 1 through 6, but 2 dice have a lot more than just 6 or 12. We have quite a few more. I'm going to draw out our sample space in a table this time instead of a tree diagram. Though a tree diagram would work, 6 branches is a lot for that tree diagram. So let's say we have the first die, 1, 2, 3, 4, 5, 6, and the second die, 1, 2, 3, 4, 5, 6. And then if we roll them together, first die is down the column, the first column, and we'll make the second across the top. I switched them when I started writing them down. It doesn't really matter, but anyways, we could have all of these possibilities. Total in the sample space, 36 possibilities. 6 times 6 is 36. But we want to know the probability of getting a sum of 7 or a sum of 11. So let's go through and see if we can figure out a sum of 7. What would that be? Well, in the first row, 1 and 6 are the only way we can get 7. 2 and 5 will give us 7. 3 and 4 will give us 7. 4 and 3 gives us 7. 5, 2, and 6, 1. All of the other numbers are either smaller than 7 up top or bigger than 7 below. How about 11? Well, using numbers from 1 to 6, there are 2 ways to get 11, 6 plus 5, or 5 plus 6. So we can come up with this compound event, probability of sum of 7 or 11, by looking at it separately. Sum of 7, sum of 11, and we'll talk more about this word or. Or is a special word in statistics. So we'll talk a little bit more about that later and why we can add these together. And looking at this, a sum of 7, we have 1, 2, 3, 4, 5, 6 out of 36 possibilities. And then a sum of 11, there's 2 out of 36. And we add these together, they have the same denominator, so we can keep that denominator. 6 plus 2 is 8. And then if we reduce the fraction, I see that I can divide top and bottom by 4. And I get 2/9. If you were to try to do it on your calculator, you get 0.222 repeating forever. So keep it as a fraction, it's okay. But this would be our theoretical probability of getting a sum of 7 or 11. And remember, theoretical, classical, they mean the same thing. You try this next problem on your own. See if you can come up with the probability of drawing a blue marble from a bag containing 2 red, 3 blue, and 5 green. And now let's take a look at this last problem in this part of our lesson, dealing with the empirical probability. Of 1,338 people who came to a blood bank to give blood, 253 people had high blood pressure. Estimate the probability that the next person who comes in to give blood will have high blood pressure. Recall that empirical probability deals with past data, or instances that have already occurred. We have a situation where 253 had high blood pressure out of a total of 1,338. And so this is how we will calculate our empirical probability. We take how many total, so probability of the next person has high blood pressure. We'll take the 253 who have high blood pressure out of the total number of people who came. And if we do that calculation, we can pull up our calculators. 253 divided by 1,338, and we get 0.1890. 3 decimal places is good. That 0 will just mean we stay at 9. Or if we wanted to write it as a percent, remember that we multiply by 100%. Multiplying by 100 will give us 18.9. And just remember to include that percent symbol on the end because 100% is a special form of 1. And that's how we'll calculate empirical probability. How many total did we have before of our desired quality divided by how many total occurred altogether. In the last part of this lesson, we'll talk about complements of events and look at something called a Venn diagram.